All right, part one of part two, because this is just a lot to really kind of absorb. This is one of the last lessons from 3 that we'll do for you senior math 2 kids. So here we go. We're going to talk about rational and irrational numbers. We're going to talk about complex numbers. What happens when we have the square root of -1? How do we rewrite those numbers? And so let's just go here. Problem number 1. It says, verify that these are equivalent. Well, we're going to take Mr. Wilson's word for it, that they're equivalent, which they are. It says, plot the solutions on the number line. Well, remember, in order to solve, we have to take a standard form and put it in factored form, and then we set all of our factors equal to 0. So x minus 5 halves equals 0. That should be 5 halves, not 5 over 5. And x plus 3 halves equals 0. When we solve, we move everything over to the other side. Well, 4 equals 0. That's actually a factor, but it doesn't equal anything. X is going to be equal to positive 5 halves, or x is going to be equal to negative 3 halves. If we add 5 halves to both sides and subtract 3 halves. Where does those numbers go on the number line? They go at negative 1.5. or negative 1.5, or they go at positive 2.5. So this is 5 halves, or 2.5. Right? Those are actual, they're decimals, but they're actual physical whole numbers. Well, what would happen if we solve this quadratic function? Well, if we went through the quadratic formula, we would end up with 2 factors like this. And again, we set each factor equal to 0. So minus 2 plus the square root of 2, or minus 2 minus the square root of 2 equals 0. Here's both of our factors. Set them equal to 0. Let me rephrase that, sorry. We're setting our factors equal to 0. Goofed on that one. Here we go. X, no. Yeah. X minus 2, oh, batting 1,000 in this one, plus the square root of 2 equals 0. Or, I think that's what I meant to write, x minus 2 minus the square root of 2 equals 0. And again, when I solve, I'm going to move the negative 2 over to the other side. So x is equal to positive 2. And what happens when I move plus the square root of 2 over to the other side? I get minus the square root of 2. Or, I get positive 2. And this minus the square root of 2 becomes plus the square root of 2. So I get or. Now those are my exact solutions. Well, I still don't know where to put them on the number line. Okay, well the square root of 2 is approximately 1.41863 blah 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 blah. We use 1.4. This is all we use. So this becomes 2 minus 1.4 or 2 plus 1.4. Or 0.6, or 3.4. So 0.6 is a little over halfway in between. 3.4 is a little less than halfway between. So that's where those goes. Now, I put these up on the number line, but remember, I only approximated them. These are the exact solutions. These are the estimated solutions. The more numbers I use, the more accurate my answer would be. Okay? So that's kind of the gist of that. Now, you might have found it difficult to locate the exact points. Well, yeah, because I couldn't locate them, but I approximated them. In this example, we're going to use find the perimeter of a triangle. Now, this is off topic a little bit, but you'll see the connection here in a little bit. How do I find the hypotenuse of this triangle? Well, a squared plus b squared equals c squared is the Pythagorean theorem. You might have heard of Pythagorean theorem. You've used it, but you don't remember. Okay, well, here's to remembering. A and B represent the legs of a triangle. So 1 squared plus 1 squared equals c squared. 1 squared is 1, 1 squared is 1, and that's going to be equal to c squared. 1 plus 1 is 2, 2 is equal to c squared. How do I get c by itself? I take the square root of both sides. So c equals the square root of 2. Some of you might say c equals plus or minus the square root of 2. Well, yeah, you're exactly right, but we don't worry about the negative radical because distance can't be negative. Perimeter is equal to 1 plus 1 plus the square root of 2. Why? Because how do I find the perimeter? I add all the sides. The only sides I can combine are 2 plus the square root of 2. Now this is the exact answer. But from the previous answer, the square root of 2 is 1.4. So this is like saying 2, and here's the other thing I want to express. Most of you might not know, square root of 2, is that, how do I know that that's a legitimate answer? Well, it's got to be greater than 1, because the hypotenuse is always the longest side of a triangle. If the square root of 2 is approximately 1.4, that's a reasonable answer. So 2 plus 1.4 is 3.4. That would be the perimeter. Again, exact answer, estimated answer. All right, well, I'm not so worried about the exact answer, but we can use it. Now let's continue. We might approximate the perimeter of a triangle with a decimal or a number. But the exact perimeter is 2 plus the square root of 2. Again, that's exact. We approximated it with a whole number, 3.4, but we also have exact. Okay? Explain how we'd use the diagram to locate two solutions to the quadratic function that we gave in the previous two questions. How am I going to use this circle? Well, this is kind of how we have to figure this out. We're going to assume that the x-intercepts of my quadratic function there and here are my quadratic function, and that my line of symmetry is at 2. That goes down the middle. Now, why didn't they include this in this diagram? Because look at this. This is a mess. It's a hot mess. There's a whole bunch of stuff here. So what I'm going to end up doing is I'm going to end up getting rid of the quadratic function, and what you should know is that the x-intercepts right here and here are on that parabola. Well, I got rid of the parabola and drew a circle. Why did I do that? I drew a circle with a center at 2, okay? And in this case, the x-intercepts, and I'm going to say plural in this case, are decimals. You would agree. The first one is a little more than a half, and the second one is a little over 3. But where exactly are they? I don't know. You can use the principle of a circle, and remember, I have a leg of 1 and a leg of 1 to find this side, which we know is the square root of 2. What does that have to do with this situation? Well, in a circle, we have a radius. And that radius is from the center to an edge, I would say a side, but circles don't have sides, an edge of a circle. So if that's the case, the distance from the center to the side of this circle, whereas the x-intercept of my parabola would be the square root of 2. So I'm going to go out to the center of the circle, which is at 2 and 0, and then I'm going to go plus 2. So I went out to the center of the circle, and I'm going to go plus the square root of 2. That is one x-intercept, and 0. The other x-intercept is I'm going to go out 2, but I'm going to go back the square root of 2. So minus the square root of 2 and 0. And there's my x-intercepts. I used the triangle because how else would I find the radius of the circle other than drawing a triangle? That's using principles of geometry to help me with algebra. All right? Are the numbers we have located on the number line in this way rational or irrational? They're irrational. Why? Because irrational numbers are decimals. They're irrational. Why? Because radical 2 is a decimal that doesn't stop. Yeah. It doesn't stop or repeat, just like the first question we did, 1.5, that stopped, or negative 0.6, that stopped. This doesn't stop. Why? Because it actually is a bunch of different decimals, like pi. Everybody knows pi is 3.14, but no, pi is an irrational number. We posit and stop it at 3.14 because most of the other stuff, we don't need to be that accurate all the time. We're going to talk about the difference between rational and irrational numbers. It wants us to pause and reflect. We're not going to. And we're going to come to here. In the previous lesson, to be determined, or in previous lessons, we found answers that dealt with negative radicals. Okay? Back then, I told you, we're not going to worry about that. We're going to save that for a later date. Well, today is the later date. Because the square root of a negative number has no defined value, it is neither rational or irrational. Therefore, it is called complex. Well, this guy Euler proposed a new number, I, to be equal to the square root of negative 1 be included, and this became known as the complex number system. Based on Euler's definition, which all you need to know is Euler was the guy that really pushed the issue of pi, he pushed the issue of negative 1, and he pushed the issue using function notation f of x. Based on this, what would the value of I squared be? Well, if I equals the square root of negative 1, then I squared is going to be equal to the square root of negative 1 times the square root of negative 1. Okay, I get that, but what is the square root of negative 1 times the square root of negative 1? That's two of the same number underneath the radical, therefore I get to take one out, so that's negative 1. I squared is negative 1. Now we're beginning to look at how do we deal with the imaginary numbers, and we're going to deal with them on a basic level, not a complex level. Okay? They're complex numbers, but we're going to deal with them basically on a basic level. The good news is, how do we deal with them? We deal with them the same as we do real numbers. There's a little bit of a twist, and you'll see that coming up in a second. So the square root of negative 2 times I squared. How do I deal with that? Well, the square root of negative 2 times I times the square root of negative 2, or square root of 2, sorry, times I. I'm going to regroup these. The square root of 2 times the square root of 2 times I times I. Two of the same number, they're both radicals. This becomes 2, this becomes I squared. Here's the difference. I know based on what I did up above that I squared is equivalent to negative 1, so I'm going to substitute. I squared is negative 1, so my actual answer is negative 2. Apply that philosophy over here. 3 times 3 times I, or 9 times I squared. I squared is negative 1, so 9 times negative 1 is equivalent to negative 9. The imaginary parts became real. It happens. Okay? Again, more practice in how we deal with that. I'm not going to go through all of these, but I will go through a couple of them. How do we add parts? We have imaginary and real parts. Well, I'm going to add the real parts. 13 minus 12 is 1. 2i minus 5i is negative 3i. Again, you see it's kind of like treating the I kind of like x. Down here we have minus positive 7 and minus a negative 3, so that becomes minus 7 plus 3i. 8 minus 7 is 1. Minus 1 plus 3 is plus 2i. That's how you simplify those. And we can also multiply them. How do I multiply them? Well, 3 times 4 is 12. 3 times 2i would be 6i. 4 times negative 5 would be negative 20i, and so on. And we combine these two. So 12, and this is the last thing I'm going to talk about in this video because it's going to be kind of long, and I don't want it to be. So plus 6i minus 20i minus 10i squared. Alright, so I've done all my multiplication, and I add all four together. Well, 12 minus 14i, right, because you combine like terms, minus 10i squared. From before, I squared is negative 1. So 12 minus 14i minus 10 times negative 1. And this is where the imaginary part disappears. At least part of it does. So I get 12 minus 14i plus 10. Turned real, combined your real parts, 22 minus 14i. There. Ask questions as you need to. I know that's a lot.